Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you enjoy the podcast, show your support with a like, a follow, or a comment. It's free for you, but means the world to us. Let's keep leveling up together.
Today, we are undertaking a deep dive into what we consider, one of the ultimate engineering challenges, achieving and maintaining mechanical integrity, especially in extreme fluid systems.
Right. And we're going to be focusing on the parts people often forget about, the real unsung heroes.
Exactly. We're talking about seals and joints. They seem so simple, but these are the linchpins that determine whether a high-performance system actually holds pressure and, survives its mission.
And it doesn't matter if it's a deep-sea submersible or a high-thrust rocket engine.
Yeah.
Right. The principle is the same.
The principle is absolutely the same. Failure at a joint is still failure.
Absolutely. And when we talk about engineering seals, I think it's important to stress we're not just talking about a simple rubber ring you pick up at the hardware store.
Oh, not at all. We are operating at this really intense intersection of material science, high-stress mechanics, and of course, thermodynamics.
So our mission today is to pull key insights from engineering handbooks and some specialized failure reports to answer the questions that I think keep real engineers up at night.
Questions like, how do we maintain contact on a dynamic surface without causing catastrophic wear?
Or how do we stop differential thermal expansion from literally tearing fixed joints apart?
And the big one, what materials actually deliver when the temperature hits 4 figures?
We're looking beyond the basic components then. We're getting into the truly deep engineering considerations.
That's the plan. That means analyzing dynamic contact surfaces, assessing high-performance fixed joints like welding and diffusion bonding, really understanding material resilience.
And learning precisely how material selection, and we're talking everything from specialized steels to nickel superalloys and composites, how that selection dictates whether a system can truly survive in these extreme temperature and corrosive environments.
It's a huge topic.
It is. So we've got a massive amount of material to cover, but it all starts where the action is, with movement. We're jumping straight into part one, the critical engineering of dynamic seals. Let's start with, I guess, the non-negotiable mission statement. What is the fundamental goal here?
The foundational goal of any seal, whether it's static or dynamic, is it's simple to say, but it's incredibly complex to execute.
Okay.
A seal must possess adequate deflection and resilience capability to provide the dynamic seal contact required to control leakage throughout the entire range of operating conditions.
The entire range, that's the key phrase right there.
It is. This means it has to work perfectly at system startup, at shutdown, and during every single high-pressure transient in between.
It's easy to seal something that's static, right? You just bolt it down tight and call it a day.
Sure.
But the second you have a shaft rotating or a piston moving back and forth, you immediately introduce wear and friction.
Instantly. And the definition of seal performance goes far beyond just controlling the fluid. We have what you could call a triple threat of failure criteria that engineers absolutely must address.
A triple threat. Okay, let's break that down.
We have to. So engineers must manage 3 distinct criteria throughout the operating life of the component. And the tricky part is that managing one often compromises another.
Ah, the classic engineering trade-off.
Always. The first and the most obvious one is that seal wear shall not result in excessive leakage. If the system leaks, the seal has failed its primary function. It's a pass-fail.
Right, that's what everyone thinks of. But the next 2 criteria often get overlooked by people outside the industry. The seal needs to perform without, destroying the very system it's supposed to be protecting.
Exactly. The second criterion is that the wear must not generate excessive friction.
Why is friction such a big deal? I mean, some friction is unavoidable, right?
Some is, but excessive friction is a massive system loss. First, it generates heat, which can lead to thermal degradation of the fluid or even the seal material itself. Second, it consumes power, which just decreases the overall system's efficiency.
And in really high-speed systems, I'd imagine that friction can be the ultimate limiting factor on speed and durability.
It absolutely can be. And then there's the third criterion, which is critically important in clean systems like those handling propellants or high-purity chemicals.
Okay.
Wear must not result in contamination. If the seal material itself abrades and starts shedding little particles into the fluid, you're in big trouble.
Because those particles can clog filters, right? Or damage pumps.
Clog filters, damage pumps, or just contaminate the end product, rendering the entire system useless no matter how well it holds pressure.
That contamination factor is often an absolute showstopper. Okay, so now that we know the mission, let's talk about the sharp end of the stick. the contact surfaces. This is where the physics of the seal material meets the engineering of the hardware. What's the delicate design imperative here?
The design imperative is a very tight balance between two competing requirements.
Another trade-off.
Of course. The sealing contact surfaces must provide the required degree and extent of contact, which means high enough pressure across a broad enough area to stop the fluid.
Okay, that makes sense.
While simultaneously minimizing friction and minimizing wear over the entire operating life.
So that sounds like a fundamental compromise is engineered right into the system from day one. You need pressure to seal, but that pressure generates the friction and wear that leads to inevitable degradation over time.
That's the paradox.
So what happens when engineers try to analyze this? How do they predict performance?
Well, when dealing with dynamic analysis, especially for something common like O-rings, a lot of the initial work is empirical. It's driven by decades of rigorous testing.
Meaning you can't just calculate it from first principles?
Not easily. Engineers need specific, validated design data that correlates dynamic interface leakage to two key variables, the surface topography and the bearing stress.
Let's unpack those. Surface topography. That's just how smooth the moving part is, right?
Exactly. The finish of the moving hardware. How smooth or rough the piston or the shaft is. And the bearing stress is the actual pressure the seal exerts against that surface.
So if the machine shop that's delivering the piston rod changes its polishing process, even slightly,
it could immediately invalidate all the leakage predictions, even if the seal material remains exactly the same. The surface finish is just as critical as the seal material itself.
that's a huge insight. It's not just the seal, it's the entire system interface.
Absolutely. And this leads us directly to stress management at that interface. Engineers have to calculate and ensure that the sealing interface bearing pressure, whether it's at a static rest point or a dynamic motion point, is high enough to effectively control that leakage.
But there's a limit.
There's a hard limit. They must never allow that pressure to exceed the material yield properties of the seal material.
What happens if it does?
If the localized pressure is so high that it permanently deforms the elastomer or the plastic, the seal loses its ability to rebound. Its resilience is gone. Performance just drops off a cliff.
Once you've yielded the seal, it's trash.
It's done. You have to replace it.
Okay, let's move to the materials that deliver this performance. Elastomeric and plastic seal resilience. The O-ring is definitely the workhorse of the industry. Why is it so dominant beyond just its simple universal shape?
The O-ring is dominant because its resilience properties have been derived extensively by empirical methods for very specific configurations over decades.
So it's all that historical data.
It's a massive, reliable database. Engineers know what a standard O-ring made of a specific compound will do when compressed in a specific groove under predictable pressure and temperature conditions. It minimizes the need for complex analytical design for most standard applications.
That standardization and reliability based on decades of industrial testing, that makes it the attractive go-to choice. It's a known quantity.
Precisely. That said, if you design a novel seal geometry, something brand new, you can't just look up its resilience properties in a standard chart.
Right. There's no data for it yet.
Exactly. New seal configurations, unsupported by reliable empirical data, must undergo extensive testing to ensure they conform to the design requirements. The design practices might guide the initial geometry, but the actual resilience properties for novel elastomeric and plastic seals are confirmed primarily through empirical methods specific to that one configuration.
So if a company invents some new seal shape that's optimized for a unique valve, they are basically signing up for a significant and probably expensive testing and certification process before that seal can be trusted in any critical application.
Absolutely. They're starting from scratch. Now, consider the designs that are inherently more complex than a simple toroidal O-ring. When you look at configurations like lip seals, cup seals, or mechanical face seals, they require extensive design analysis and specific testing before you can even think about deploying them.
Let's focus on the face seal analysis. That sounds like a great example of dynamic complex engineering.
It is. Face seals are often used for rotating shafts, and they work by maintaining contact between two perpendicular faces.
Okay, but how do you guarantee that contact when things are vibrating or heating up and expanding?
To ensure constant contact, they typically rely on a secondary element, often a metal or composite bellows. The analysis for these seals demands evaluating that bellows deflection under all operating conditions.
So the bellows essentially acting as a very carefully calibrated spring, maintaining the pressure between the two faces.
Exactly. If the primary system structure expands or warps due to temperature shifts, the bellows element must provide the correct deflection to maintain that critical interface pressure.
And the analysis has to cover both extremes, I imagine.
It does. The analysis ensures the bellows isn't overstressed or crushed, but it also confirms it provides sufficient spring force to follow the inevitable movement of the shaft and the housing.
And that concept of managing movement, whether it's a tiny bellows or the full thermal expansion of a massive piece of machinery, perfectly guides us into part 2. This is where things are not supposed to move at all. Fixed joints and material compatibility in fluid systems.
Right. Fixed joints are the absolute bedrock of any system architecture. They are defined as non-separable connections, and they're essential in fluid system components because it's just impractical to make entire line assemblies in one single piece.
Plus, you always have assembly and installation clearance problems that force you to use a joint.
Always. You can't snake a 20-foot piece of bent tubing through a crowded engine bay.
But, as you pointed out, the goal is always to keep the number of fixed joints to an absolute minimum, while the inherent distrust of joints, even permanent ones.
Because every single fixed joint introduces complexity, it significantly increases cost, and critically, it affects the overall reliability of the system.
Every joint is a potential failure point.
It's a potential leak path, a site for corrosion, or a point of stress concentration. A system designer who can replace 5 joints with a single well-designed piece of tubing has massively improved the reliability curve of that system.
When we talk about high-performance fluid systems, especially in aerospace or chemical processing, what is the default, the gold standard method for achieving a permanent connection?
Welding. It remains the most common and robust method for joining tubular components, particularly in demanding propellant systems.
And why is that? What makes them so good?
Welded joints exhibit excellent mechanical properties and superior environmental and propellant compatibility characteristics. And within the world of welding, there is a strong preference for butt-welded joints.
Okay, so when does an engineer choose a butt weld over other potential fusion methods?
Right.
What is the core engineering advantage there?
Butt welds are preferred primarily because of 2 key benefits, and they're related to inspection and integrity. First, they allow for straightforward radiographic inspection.
X-raying the weld, basically.
Exactly. You can fully scan the integrity of the entire joint without any obstruction, ensuring the weld penetration and quality are uniform all the way through. And second, and this is critically important, they lack built-in crevices.
Tell us more about the importance of avoiding crevices. That sounds subtle.
Crevices are microscopic traps. They can harbor static fluid or contaminants, which, in a dynamic fluid system, leads to concentration effects.
What kind of effects?
If you have a corrosive fluid, the concentration of corrosive ions or their reaction byproducts within that tight little space can dramatically accelerate localized corrosion, what we call crevice corrosion, which leads to a premature and often catastrophic failure. Butt welds completely eliminate that geometry.
I noticed the source material also mentions sleeve welds. When would an engineer opt for a sleeve weld? It sounds like it intentionally creates more geometry than a simple butt joint.
It does, but sleeve welds offer a specific utility. They provide a significant advantage for self-aligning components, and they're fantastic for in-place repair or modification.
For field work.
Precisely. This design allows technicians to cut out a damaged section of tubing and replace it using a sleeve insert. This speeds up assembly, and it eliminates the need to trim an exact, perfect length of pipe in the field, which can be very difficult to achieve under tight clearances.
So the butt weld is the standard for original manufacturing because of its integrity, but the sleeve weld is the practical hero for field maintenance and quick modifications.
That's a great way to put it. Now, shifting focus completely, we come to soldering. It seems counterintuitive to use soldering in older, low-strength technique in high-performance contexts. Was it just a historical anomaly?
I was wondering about that. It seems a bit weak.
Not entirely. Soldering has historically been used in low-pressure applications where accessibility and speed were essential. For instance, the Apollo spacecraft utilized soldered joints extensively in its low-pressure sections.
How many are we talking about?
Over 1,500 plumbed joints.
Wow. That is a staggering number of critical, non-separable connections relying on a low-pressure bond in those critical missions ever attempted. What were the inherent advantages there?
Well, solder joints are relatively simple. They require basic heating tools, and they are readily made in place without the need for complex inert gas shielding, which you need for high-strength welding.
So it's easier and faster. But what are the downsides?
The main restriction is that they are strictly limited to lower pressure systems, and there's a real risk of the filler metal flowing too far internally and causing a flow blockage, especially in small diameter tubing. You sacrifice pressure capability for ease of manufacturing.
That risk of blockage is a severe limitation. Okay, let's move to a more modern, advanced method that solves the compatibility problem, diffusion bonding. But this technique introduces a major headache: the coefficient of thermal expansion crisis.
Yes, diffusion bonding is a solid-state joining method. It doesn't melt the base metals. It was developed primarily for joining materials that are metallurgically incompatible and thus extremely difficult or impossible to weld directly.
Like what?
The classic example is titanium to stainless steel transition joints. These were used extensively across early space programs like Gemini, Apollo, and Surveyor.
So you solve one problem, joining two incompatible metals, but you introduce the ultimate physics headache: the CTE mismatch. Explain the coefficient of thermal expansion, or CTE, crisis in detail.
The CTE crisis occurs when you couple materials that expand or contract at widely different rates when they're exposed to thermal cycling. Think of a system that goes from ambient temperature on the launch pad to ultra-hot or cryogenic operational temperatures in space.
And this differential movement between the two components causes immense internal stress.
Exactly. And what's the mechanical consequence in, say, a bolted coupling?
I'm guessing it's not good.
It's terrible. If the coupling housing material has a high CTE and it contracts rapidly when the temperature drops, but the bolts holding it together are made of a low CTE material, the coupling shrinks much, much faster than the bolts.
And that differential movement can dramatically loosen improperly preloaded bolts.
It does. The bolts lose their vital clamping force just when the system needs them the most, when temperatures are low and the system is under maximum stress. That can lead to immediate leakage or even a rupture failure.
This improper clearance or fit causes severe operational problems and defects. The system can't maintain its structural integrity under thermal cycling because the bolt preload, the very foundation of the design, is compromised.
Precisely, which means the mitigation strategy is absolutely critical.
What is that mitigation strategy? How do you fight physics?
You don't fight it, you design for it. Engineers must minimize thermal stresses by one of two methods. The ideal scenario is simply using materials with very similar CTEs across the entire joint.
But that's not always possible, right? Especially when joining exotic metals.
Often it's not. In that case, they must perform a detailed structural analysis to determine the exact proper bolt preload required before assembly.
So you calculate the inevitable expansion and contraction effects across the full operating range, and then you set the initial clamping force high enough to ensure that even at the lowest temperature and the lowest resulting clamping force, the joint integrity is still maintained.
It results in an explicit thermal compensation strategy built right into the mechanical design. You are engineering around the physics of thermal mismatch by calculating the precise thermal movement and compensating for it mechanically.
That level of meticulous calculation brings us beautifully into part 3, material selection, the foundation of durability. When you're dealing with extreme temperatures, hostile fluids, or high stress, you just can't rely on common alloys. We need to talk about the high-performance materials.
Right. And high-strength nickel alloys are fundamental here, particularly for critical fasteners and structural members exposed to corrosive or high-temperature environments. We can categorize them by their primary function and their temperature range.
Can you categorize some of those major players for us?
Sure. We're primarily looking at the nickel superalloys. For specialized applications that need wide thermal stability, you have alloys like Rene 41. It's used across a huge range from cryogenic temperatures all the way up to 1200 degrees Fahrenheit. These alloys maintain their strength in the face of massive thermal variation. Then, for structural components that need to withstand even higher thermal loads, you transition to materials like Inconel X750, which takes over at the high end, covering the range from 1200 to 1600 degrees Fahrenheit.
And there are others too, right?
Oh, yeah. Other general service high-strength alloys include A286, Inconel 718, and K-Monel.
That ability to function consistently across thousands of degrees Fahrenheit is what defines these materials. They maintain their structural integrity where standard steels would just instantly creep or fail.
Absolutely. Now, let's specifically discuss Inconel Alloy 600, which is often considered a standard engineering material despite its, specialized performance.
What makes Inconel 600 so universally valued?
Its core strength is its resistance to oxidation up to an incredible 1177 degrees Celsius or 2150 degrees Fahrenheit. It is valued for its strength, its workability, and its unique corrosion resistance profile.
What's so special about its corrosion resistance?
Crucially, it is known for its resistance to chloride ions, stress corrosion cracking, and general corrosion by high-purity water.
That specific resistance profile immediately points to certain massive industrial applications.
It does. It makes it an indispensable component in nuclear reactors, where it's often designated as Inconel alloy 600T for that service. It's used extensively in heat exchanger tubes and steam generators, where it has to withstand continuous exposure to high-temperature, high-pressure water without failing.
Before we move on, let's touch upon surface protection, because even these superalloys need some help to function efficiently, especially when they're being used as fasteners.
Right. Surface protection is non-negotiable for critical fasteners, for both compatibility and function. Silver plating is widely used on bolts and nuts.
And what's its purpose?
It's twofold. First, it solves general fluid compatibility problems. Second, and very practically, it reduces friction during tightening.
Why is reducing friction during tightening so critical?
Because bolt preload, that required clamping force we talked about, is highly dependent on the friction between the threads. If the friction is too high or unpredictable, you can't be sure how much of your torque is actually stretching the bolt versus just overcoming friction.
I see.
Silver plating provides a consistent, low-friction surface. It ensures that a measured torque translates reliably into the intended clamping force, allowing the engineer to achieve the necessary preload calculated to withstand external stresses and that thermal movement.
We also noted a very specialized surface protection strategy for liquid oxygen systems.
Yes. Liquid oxygen is a powerful oxidizer, and any traditional hydrocarbon-based lubricants are an explosive hazard. So a special challenge arises: ignition compatibility.
You can't have something that might spark.
Exactly.
Yeah.
To solve this, specialized dry film lubricants, specifically phosphoric acid-bonded lubricants, are used because they are chemically inert and prevent the ignition risks associated with that high oxygen environment.
Okay, moving on to more foundational materials. What is currently driving innovation in structural steels?
One of the major recent advancements in metallurgy is the development of dual-phase steels. These are produced by rapidly cooling a medium carbon steel that contains elements like vanadium or molybdenum. This controlled process results in a very specific heterogeneous microstructure.
And what does that microstructure martensite islands in a ferrite matrix actually do for the steel? What's the benefit?
It creates a material that exhibits continuous yielding behavior during deformation. That means there's no distinct yield point. This provides increased uniform elongation and enhances work hardening.
Okay, translate that for me. What's the critical engineering implication?
The implication is that these components actually gain strength during the forming operation, like stamping or bending.
That is a phenomenal property.
Yeah.
It gets stronger as you shape it. That must mean less waste, fewer material failures during manufacturing, and a much more predictable final component.
Absolutely. That's the real insight here.
Okay.
It's why they are applied in high-impact critical locations like automobile wheel rims, where energy absorption and predictable strength are paramount.
Let's look at aluminum alloys now. We know they offer a superior strength-to-weight ratio. But what other characteristics make them so indispensable in high-performance structures?
Beyond the strength to weight, alloys like 7075T6 offer two specific advantages. First, general corrosion resistance, which makes them ideal for things like roofing, pipelines, and packaging.
And the second?
The second, and this is crucial for fluid systems, is good cryogenic properties. Unlike many materials that become brittle at low temperatures, the mechanical properties of most aluminum alloys actually improve as the temperature decreases.
So they're essential for handling things like liquid hydrogen or other cryogens. Now, for those of us trying to decode alloy specifications, how does the wrought aluminum designation system work?
It's a 4-digit system used to logically categorize these massive families of materials. The first digit defines the major alloying class. For example, the 7XX series indicates aluminum zinc alloys, which are known for achieving very high strength.
Okay, what about the other digits?
The second digit defines variations in the original basic alloy. 0 is the original composition, 1 is the first variation, and so on. The last two digits designate the specific alloy within that series, though they don't necessarily have a sequential significance.
Finally, we reach the frontier of materials: composites and ceramics for advanced sealing environments. When engineers look at ceramics, the design philosophy itself has to change fundamentally.
It does. We shift from what's called deterministic design, a single valued strength, to probabilistic design. Ceramics are designed to a specified probability of failure.
Why the reliance on probability? Why can't you say it has a strength of X?
It's due to the general lack of plastic flow in ceramics. They don't yield like metals do, because their strength is highly dependent on microscopic internal flaws and crack sizes introduced during manufacturing. Their strength exhibits a wide statistical variation.
So we can't guarantee every single part is as strong as the next.
Exactly. Engineers must statistically account for this inherent brittleness in design within an acceptable probability that a failure-inducing flaw won't be present at the operational stress level.
But despite their brittleness, they thrive in high heat, high wear applications.
They do. They retain their hardness under extreme conditions. High-temperature ceramics, specifically the alumina and silicon nitride families, retain significantly higher hardness at temperatures between 600 and 1,000 degrees Celsius than conventional tool steels. This makes them ideal for high-speed cutting tool inserts and abrasive environments.
And composites bring their own tailored properties to the table, solving problems like that CTE crisis we discussed earlier.
Composites offer a level of tunability that metals simply can't match. Polymer matrix composites, or PMCs, reinforced with materials like carbon and aramid fibers or silicon carbide particle reinforced aluminum, can be specifically tailored for extremely low coefficients of thermal expansion.
That dimensional stability is the key takeaway here. If you can build a structural component with a near-zero CTE, it simplifies or entirely eliminates the need for that complex thermal stress analysis in fixed joints.
It drastically reduces thermal stress management issues. Furthermore, their tunability extends to thermal conductivity, which is vital for thermal management.
How does their conductivity compare to common metals?
While some composites can achieve thermal conductivities as high as 980 watts per meter Kelvin. For comparison, the thermal conductivity of pure copper is only about 400 watts per meter Kelvin.
That's more than double.
It is. By carefully selecting the reinforcing fibers and the matrix materials, it is even possible to produce composites with near-zero CTEs, providing both strength and exceptional heat management in one package.
That ability to engineer out the very problem that plagues fixed joints is a huge advantage. Okay, let's shift our focus to the mechanics of destruction, or part 4. Failure models and stress analysis in detail.
This is where we analyze how these highly engineered components actually fail under stress, temperature, and time.
Let's start with high temperature failure. Creep and stress rupture. Fundamentally, what is creep in the context of metal structures?
Creep is the progressive accumulation of plastic strain in a component that is stressed at an elevated temperature over a period of time.
So think of it as a very slow, high-temperature stretching that permanently changes the shape of the part.
That's a great way to think about it. And this eventually leads to intercrystalline failure in metals, meaning the failure starts primarily in the grain boundaries of the material.
And how do engineers break down the life cycle of creep? I know it has 3 stages.
It does. A typical creep process starts with an initial instantaneous elastic loading. This is then followed by stage 1, the primary stage, where the creep strain rate rapidly decreases over time as the material strain hardens.
Okay, and then the important one, stage 2.
Crucially, stage 2 creep is the steady state phase.
What happens during that steady state phase?
Stage 2 is characterized by a constant rate of deformation. This steady rate is usually the result of a dynamic balance between the material trying to strain harden and other processes, like recovery, that are softening the material. This balance allows the deformation rate to be constant, and most of the component's usable operational life is spent in this stage 2 phase.
And when the material enters stage 3, what does that look like?
Stage 3 is the tertiary stage. This is where the creep rate increases rapidly, accelerating toward failure. This is driven by geometric factors like necking, or more fundamentally, by the nucleation and growth of internal defects like cracks and voids.
And then eventually?
Eventually, you get creep rupture, or stress rupture. That's the point when the stressed member actually separates into pieces.
That detailed understanding of the stages allows engineers to predict the point of necessary replacement long before a catastrophic rupture happens.
Yeah.
Moving on to cyclic loading. How do engineers analyze fatigue crack propagation?
Fatigue crack propagation is modeled using fracture mechanics. The total fatigue life, which we'll call N, is defined as the sum of the initiation life, N sub I, and the propagation life, N sub P.
So initiation is the number of cycles it takes to form the first crack, and propagation is the number of cycles to grow that crack to a critical size.
Exactly.
When engineers look at the formulas that describe that crack growth, what is the core conceptual insight? Let's avoid just reciting complex variables.
The core conceptual insight is that crack growth is highly nonlinear. The rate at which the crack grows with each cycle is exponentially dependent on the stress intensity at the crack tip.
So as the crack gets longer,
The stress concentrates more and more aggressively at the tip, causing the crack growth rate to accelerate rapidly toward catastrophic failure.
and this analysis is highly sensitive to the initial conditions, I assume.
Absolutely. If the component, let's say a welded joint, is assumed to contain a pre-existing manufacturing defect, then the initiation life, N sub I, is considered to be 0.
And the engineer focuses only on propagation life, N sub P.
Right. They assume the crack starts at a measurable defect size from day one. This is a common, very conservative approach to ensure system reliability.
We've covered slow failure over time. What about catastrophic, sudden failure due to dynamic forces?
That is impact failure. It's caused by non-static loads that induce massive stress and strain waves throughout the component. The critical insight here is that these waves create local stresses that can be many times greater than what a static application of the same load would produce.
So even a moderate but very sudden dynamic load creates disproportionately high internal stress.
Exactly. If the local stresses cause the component to separate into 2 or more parts, we call that impact fracture. If the impact causes intolerable elastic or plastic deformation without separation, it's defined as impact deformation. Either way, the component is unusable.
Okay, now let's talk about proving these stresses exist. This requires experimental stress analysis methods. This is what you do when a failure isn't obviously due to a bad material batch or something simple.
Exactly. Experimental stress analysis is crucial because it detects both the external applied stresses and the invisible built-in stresses, known as residual or molded-in stresses, that are locked into the material during fabrication.
Residual stress sounds like the real hidden killer here. How do you measure something that's already frozen into the material?
One of the most effective methods is the hole drilling method, which uses strain gauges. First, you measure the stress at a specific location on the part as it is. Then, you drill a very small, precise hole there, which relieves the frozen-in stresses in that immediate area.
And then you measure again.
You remeasure the stress, and the calculated difference between the two measurements is the magnitude of the residual stress that was locked into the part.
That is a clever way to quantify the internal strain energy that might contribute to a later failure. What about plastics? They have a unique failure mode related to chemicals, right?
They do. For plastics, we often use what's called the chemical method. Stress cracking occurs when plastics that are under stress are exposed to certain chemicals that act as environmental promoters. This is actually a crucial quality control method.
Give us the classic example of PVC pipe testing.
A classic example is quality control for rigid PVC pipe, which is tested using anhydrous acetone immersion. If the PVC compound is poorly manufactured or unfused, it contains high residual stresses.
When you expose it to the acetone,
The material will swell, flake, or sometimes disintegrate completely. However, if the PVC is properly fused and has low residual stress, it is impervious. It will only show minor swelling. This quickly verifies the integrity and manufacturing quality of the pipe.
that is a great real-world example of using a chemical reaction to verify mechanical integrity. Finally, let's wrap up this part with a quick review of the mechanics fundamentals that underpin all of these analyses. We have to start with Hooke's law.
Hooke's law provides the basic framework for linear stress-strain relations. It details how stress in one direction not only causes strain in that same direction, which is defined by the modulus of elasticity, E, but also causes strain in the perpendicular direction. That relationship is defined by Poisson's ratio, V. This is the basis for all multi-axial stress analysis.
And when predicting catastrophic failure in brittle materials, like cast iron, which theory do engineers turn to?
For brittle materials, the maximum stress theory, also known as Rankine's theory, is often employed. This theory predicts failure when the maximum value of the greatest principal stress reaches the material's ultimate stress at failure.
And why does this theory align so well with brittle materials specifically?
Because brittle materials have negligible plastic flow, failure occurs very suddenly once the maximum tensile stress limit is reached, making the magnitude of that single stress the critical factor, regardless of the stresses acting in other directions.
And applying that theory practically requires defining the working stress. How is that calculated?
Yes. For brittle materials subjected to tension, the working stress, sigma W, is calculated as the ultimate stress divided by the product of the stress concentration factor, K sub T, and the factor of safety, N. That product ensures the operating stress remains safely below the theoretical failure point. factoring in both geometric flaws and the required reliability.
That brings us full circle. We started with the specific challenge of maintaining contact pressure in the dynamic O-ring, analyzing surface topography and friction management, and saw how that single requirement led us right through complex thermal management strategies in fixed joints.
And how those thermal issues push us directly into advanced material selection. We examine high-strength nickel superalloys like Inconel 600, engineered microstructures like dual-phase steels, and the unique probabilistic design philosophy that's necessary for engineering robust ceramic components that inherently lack plastic flow.
The ultimate takeaway is that engineering seals and joints is truly about managing complexity at the interface of mechanical loading, environmental challenges, and material science. There's no simple fix. Every single solution requires compensation for a potential failure mode, whether that's thermal expansion creep or fatigue crack propagation.
Right. And for a final thought, we noted earlier how some composite materials are engineered to have near zero coefficients of thermal expansion.
Okay, yes.
So if thermal expansion mismatch is a primary cause of joint failure, because that differential contraction loosens bolts and generates massive internal stresses, what applications could be revolutionized by substituting traditional fixed joints with these dimensionally stable composites? You could thereby potentially eliminate the need for complex and often expensive thermal stress calculations entirely. That's the question you should be mulling over.
And that is our deep dive for today. Thank you for listening. If you enjoyed the content and want to see these concepts in action, if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together, stays together.